Okay, welcome to this video on 2014 question B2. Okay, so the figure shows an incomplete trimetric projection. So they've given you a lot of the information already. Okay, using the Axonometric Axes method of a model of a basketball backboard based on the 3D graphic on the right. The elevations and end elevation are in their required position. Okay, so they're required position. Now, part A, draw the axonometric triangle X, Y, and Z, or the axonometric axis rather, and the scaling triangle ABC. Part B, draw the elevation and end view. Okay, orientated as shown, and complete the trimetric projection. So they're in their required positions, and they give you a hint on how to start the basketball board. Okay, in part C, draw the axon and projection of a basketball in contact with the backboard at point P, and the radius of the ball is 12. Alright, let's start at the first one. Alright, so the axonometric axis X, Y, and Z. Now, trimetric means we have three unequal angles. So we don't know those two. Now, the distance between Y and Z, the angle between that is 110. And we also know that A to B is 90. So I can draw in the y-axis. I can draw in the z-axis using my protractor at an angle of 110. Then to get the x-axis, I can measure across 90, so 50 and 40, and join the 2 points. That gets B, and I can join to there. And that gets the x-axis. Right, so I'm going to do that now immediately. So draw in my y-axis, take my protractor, measure in my 110 degrees. Okay, now point B in the triangle is over 40 from the y-axis, and point A is over 50 from the y-axis. Measure over 50 here from the y-axis. Drop it down. Horizontal line here. $90mm, and I can join back to the origin there. Okay, so that's the z-axis, x-axis, and here's the y-axis. Now, the scaling triangles. So they give you the key information in doing this. Look, if you look at the question here and on the color on the page, the z-axis is at 90 degrees to line AB, and line AC is at 90 degrees to the x-axis, and line AB is at 90 degrees to the y-axis. So that is the key in doing these questions. C to B is at 90 degrees to the z-axis, A to B is at 90 degrees to the x-axis, and A to B is at 90 degrees to the y-axis. So they're the key in completing those triangles in any type of axonometric, be it isometric, dimetric, or trimetric. So I'm going to line my set square up with the x-axis, and I'm going to bring it on there I'm going to slide it on to point A, and I can draw in what line is that? That's A to C. So then I can draw in line A to C, and then I can join it back then, once it hits the y-axis, I can join it back then to B. Alright, so I'll zoom out there a bit so you can see. So, sorry there, I lined my set square up with the x-axis, I slid it on there at point A, and I drew in the line there until it touches the y-axis, that's point C. Now, I'm ready to do part B. Okay, to draw the elevation and end view, okay, orientated as shown. Right, so I'm going to draw lines out from C and B parallel to the z-axis. So parallel to the z-axis. Right, what distance am I going to draw them out? It can be any length. I will though make it more than 90 because A to B is, A to B is 90, so I'm going to make it go out 90. It doesn't have to be 90, but it's good to use the question as a judge of space, just with your pencil while reading it, just to judge the space you can use. It can be a good idea, certainly can be a good idea. Okay, now of course in AutoCAD sometimes they can trim that, so they can. Right, what was I going to say next? Then I'm going to bring them out, drawing this line, bisect with my compass to find the center, draw in the semicircle, continue this line out until it pierces the semicircle, and there's the triangle there for it, and I'm going to do the same there. Alright, so that can be a little bit less than 90. Right, so that could be about 70. You go out there. Okay, so let's begin. Where did I put my pencil? Always have problems. Now, it doesn't have to be exactly 90. So extended on the z-axis there and went parallel to the z-axis from C and B, and now I'm drawing a line perpendicular to the z-axis, which is parallel to CB. Okay, I'm going to take my compass and bisect the line. I'll just move the visualizer now so you can see better. Okay, so I just want to get my compass. So I'm going to bisect this line now. Okay, now I'm going to draw in my semicircle then. Okay, there we have it. And where the z-axis pierces that semicircle is where you're going to draw in the elevation. There we go. Now I'm going to do the end view. So same principle again. So I'm going to draw lines parallel to the x-axis from A and B, C. Now measure about 70 out in it, about that. And then we're going perpendicular to the x-axis. we're going to bisect this line. You cannot bring that across, as that is the distance between it. This is a scalene triangle, so it's not isosceles. So I can draw in my semicircle then. Okay, and then where the x-axis hits the semicircle, okay, is the triangle that has the edge view of the vertical plane and horizontal plane. Right. Okay, so I'll pause this and label them. Okay, now we can draw these in. Right, so the question is the best source of information we have to complete it. That might sound rather obvious, but it certainly is an underlooked truth. So, alright, the center line of the basketball board happens to be on an end point of the diameter of the semicircle. Okay, we have 10, 40, and the height here, okay, is found by, okay, a point on the radius there, or sorry, this rather is the easiest one here to go to. Swinging it in. We're not given the full length of it, but it's just that distance put over onto the other side, and then the square is up 10, 40 wide, 40 high, and point P is in the middle. Okay, so we'll draw the elevation and look at the end elevation then in a moment. Right, so we'll draw in our center line. We'll mark up the heights. 10 and 40. Okay, these lines are parallel to the base. So we're going to draw lines parallel to the edge view of the horizontal plane. Now, look, that's the square is 40 wide there, and you can see the pencil mark, so it's 20 left and right of the center line, 20 left and right. So we're going to go 20 left and right. Now I can take this distance here and put it over, and then obviously parallel to the center line. Meanwhile, draw the outline for the square, so I can heavy in a square there. Oh shucks, sorry, I shouldn't have heavy that line there. I meant to go, well, it's not that heavy. I actually do need it, so okay. Now, the compass is here in the bottom. Drawing the arc. Point P, join the corners. Okay. I don't know the marking scheme off the top of my head, but they might have wanted the square in hidden detail on the basketball board, the square there in hidden detail for part C on the sphere, which is a bit in orthographic is fine. So it is, but shouldn't be so in axonometric. Okay, so I haven't gone that heavy on that line. I'll rub it out a little bit, but we'll change that to might have to change that to hidden detail later. I can't remember off the top of my head if the sphere is going to be over that line in elevation. Now, the end elevation, so a lot of students be wondering, well, where's that height from? And there's 10 and 40. Well, you take the height from here and you put it there. So I'm going to get the height there, so the radius essentially. So here's the height of the basketball board, and then we can go up our 10 and 40 and mark them in. And then a heavy line, so the basketball board projects as an edge in elevation, or in end elevation. Now, the question gives you a hint on how to complete the axonometric axis. Look, you bring these points down parallel to the x-axis, and you bring these points down parallel to the z-axis, and where they intersect, okay, you're getting the points on the the trimetric projection. So you bring them parallel to the z-axis and parallel to the x-axis. Your question is your best help to solve it. Okay, to solve the drawing, the question, exam question is your best help. So 1, 2, 2/1, okay, 3, 4, 4/3, it's 10 up, okay, 5, 6, 6/5, okay, 7, 7 there. Okay, so I'm going to bring the point 4 and 3 and 2 and 1 down parallel to their respective axes in each view. So 4 and 3 down parallel to the x-axis and down parallel to the 2 and 1 down parallel to the x-axis from end elevation or end view. Now same points again, 1 down parallel to the z-axis, 3 down parallel to the z-axis. They should be meeting on the y-axis here because they're on the edge of the end vertical plane. 5 and 6. Two brought down there, and then 4. Okay, and then we can join them together. Okay, and 7 I haven't brought down yet. Right, so the curve. How do you do the curve? Okay, well, I'll complete the square first rather before I do the curve. Okay, 9, 10, 11, 12. So I have 12/11 here and 10/9 here as well. Going to bring 9 down, 10 down, 12 down, 11 down, and to mark them in lightly here, as I'm going to have a sphere in later. Okay, the curve. Alright, so I'm going to divide, you could divide that in theory up into 60/30, but you'd be missing, you'd have to extend it on. So we'll just divide it into segments of 10. So I'm going to go up 10 here, now up another 10, and I'm going to draw lines parallel to the base. So I went up in 10s. Now, that's from I went up in 10 from 1 and 2, so I'm going to have to go up in 10s here in end elevation, because that's how you establish the points in the trimetric projection. You take heights from elevation and end elevation, or points from elevation and elevation. Okay, so label these. So C/A, D/B. Now I'm going to bring these down parallel to the x-axis. So D and B down, C and A down. Seven down, and get clean up a second, get set, go back and get 7. There's point 7. Okay, and there's A, B, C, D, which I'll freehand sketch them in a short while. Alright, what I'm going to do now is part C, the basketball board. Right, so part C, draw the axonometric projection of a basketball in contact with the backboard at point P. The radius of the ball is 12 millimeters. So right here is the ball, touching the backboard. Now, how do you get an end elevation? Take the height here, mark it on, go out 12 millimeters in your center. Draw in the ball. Okay, then bring down your center point and your center point here. You draw in the ball, and then there's your point P in end view, so you bring down point P and point P here. That's where they'll meet there inside the ball, inside it. So I'm going to do that now. Right. So the basketball has a radius 12. So I'm drawing in the ball here, radius 12. Okay, take the height from here, or it's 10 and 20. It's 30, so you can go up 30 from the base. I'm going to go perpendicular to the edge of the basketball board because it's a tangent to the sphere. I'm going to step out the radius 12. It's point P. There's my ball. There's the center point. Here's the center point as well. I'm going to bring that down. And the center point here. So there's the center point of the ball. Here's point P brought down. So there's the point of contact. Okay, and the radius remains 12 because the sphere projects as a circle in every view. Okay, sphere projects as a circle in every view. Okay, so there should be no hidden detail here because we generally exclude hidden detail in 3 dimensions. So there's the basketball board. Now I'm going to pause the video, untape my sheet and sketch in the curve, and then leave you to it, and I'll add in notes. And there we go. Cheers, thanks, bye bye.